Chhattisgarh, and my title is actually non-trivial very-phase SDH superior diffuse oscillation in single crystal nickel 3 bismuth to selenium 3, selenium 2 and calcium Zn2 Sb2. These are the different structures, and we actually mainly the talk is emphasized on the whether these two these two type of crystals are actually exhibit non-trivial topology by magnetotransport measurement. So, we know that in last decades we have tremendous work in topological material and in here we have basically two types of category, two type topological material is there. One is topological insulators and another is topological semi-metal. In topological insulator we know that we have a conducting surface state and also there is a bulk is insulator. But second one is actually topological semi-metal, and here our talk is actually in topological semi-metal. We will emphasize that how from magnetotransport studies we can understand the topological semi-metal. So, in topological semi-metal we have actually three different type of materials here, and depending upon how its conduction and band and valence band actually intersect, we have actually Dirac semi-metal where we have a point cross section intersection, and if have a two Dirac section, then we have a Weyl type of, and if this intersection is actually line or closed loop, then we have a nodal line semi-metal. So, in these two crystal is actually under in this category last one, that is nodal line semi-metal. So first I will talk about nickel 3 bismuth to selenium 3. So, these are the literature review, and we have in this type of crystal structure already known, and in nickel bismuth to selenium 3 selenium 3 or sulfide 2 we have a superconductivity, and these are the resistivity measurement, and in this measurement we can see that if it is actually sulfide, then we have a transition temperature around 0.8 Kelvin. And if it is actually selenium 2, we have actually 0.6, almost same, and these are the resistivity versus temperature and resistivity versus field. And if we have a rhenium bismuth to sulfide 2, then we do not have any superconductivity, but what we have actually at 165 we have a first order transition, and there is a structural transition, and also we have their hysteresis in the resistivity data, which is somewhat like a CDW. Next. So, if in palladium bismuth to selenium 3 also we have a superconductivity, and here from SDH oscillation we have a very nice very phase, and that is actually we have from Landau fit, actually we have a 4 different frequency, and if we have a Landau Venn diagram from that we can understood that this type of palladium 3 bismuth to 3 is actually have non-trivial very phase. And in nickel bismuth to selenium 3 we have a some planar Hall effect, and from this planar Hall effect is reported that this planar effect is from the because of the anisotropic magnetotransport resistance, and there is no DFT and air phase data in this nickel 3 bismuth to selenium 3. So, we are actually we grow a very nice single crystal of nickel 3 bismuth to selenium 3, and this is actually our Ritwil refinement, and from Ritwil refinement we understood that actually this is impurity free sample, and this is our powder excellent of single crystal sample, and here we can see that we have a 0,0 OL growth direction. And this is actually a monoclinic structure and C2 by M, and so we have actually inversion symmetry, which is also one of the ingredient to understand the to realize the topological semi-metal, nodal line semi-metal, and these are the lattice parameter. This is atomic position, and we have actually EDAS spectra. From the EDAS spectra we actually understood that the stoichiometry is actually proper in our this type of single crystal, and this is this crystal structure. And now coming to the transport measurement, we have actually Hall effect data, and in this Hall effect data, this Hall effect is actually linear, up to 2 Tesla magnetic field. So we actually fitted with the one band model, and from one band model, and then actually we saw observed that after some magnetic field 2 Tesla, this is not actually well fitted. So we fitted with a 2 band model, and this is the nicely fit up to 9 Tesla. And we saw that these are the carrier concentration. This is actually electron concentration and hole concentration, and also this is actually mobility actually plotted from this from this data. And we actually saw that they almost actually electron concentration and hole carrier concentration is almost same, and this is also we actually theoretically also calculated by bootstrap calculation, and from bootstrap calculation is also almost same as our experimental data. So this is n is by n is equal to 1 for perfect, but we have a little bit more. So this is actually now resistivity data, rho axis data versus as a function of temperature, and we have actually to understand its scattering mechanism. So we fitted with the BGM equation. This is Bloch-Grünissen-Mott model, and here this is actually Mott term, and we saw that the data is fitted very well. So we understood from these fitting parameters that this is actually have electron phonon scattering, and also we have a Mott interband scattering. This is our MR data, and from MR data the MR percentage is very small, and this data is actually we fitted with the Kohler's model, and here in principle that this shows that this MR can be represented by this B by rho. This is universal form, and if this data is actually collapsed, if it is not collapsing, so that means that there we have a multiple scattering mechanism present here. So if we change little bit, so if we introduce a thermal charge carrier parameter NT, then these actually these curves are actually collapsing at one point. And this is actually observation of weak anticoagulation. This is conductivity data, conductivity versus field, and we know that if we have at zero magnetic field, if we have a peak in conductivity, so this is somewhat like a weak anticoagulation. So we observe weak anticoagulation, but this is not a very sharp peak. So we have actually some bulk status also there. So this is actually modified. We fitted with modified HLN fit, and this is the weak anticoagulation data. From this actually we have two parameters actually, alpha, which is P factor, and it is coherence length, and actually if this coherence is actually fitted by T to the power minus half, then this is a 2D electron interaction is there, and this is somewhat different. So it is actually there is a 2D-dimensional electron interaction is there, but still there is something else also. And there is a nice theoretical paper which says that if this 2D conductivity data is actually fitted by the follow the LAB, follow LNB, then this is actually topological semi-metal, so nodal line semi-metal. So in our case this data is actually follow LNB rule rather than B to the power half. So we have to do weak anticoagulation, and this is one of the signature of the topological nodal line semi-metal. So from this also we have calculated a few parameters like AE, AEP, EP, and these are telling that whether is electron interaction is there or electron phonon interaction. So next we have a Subintikov Diaz-Boas oscillation. So this is very important because from Subintikov Diaz-Boas oscillation actually we can understood the topological pi Berry phase. So our data can be fit with this formula. And we have a two part actually RT temperature dependent part and actually field dependent part, and for this from Dingle analysis also we can understood that its effective mass we can calculate from this Onsgaard relation actually. So we let's see whether we have a pi Berry phase or not. So this is our del sigma x divided by delta v versus 1 by plot, and we see that this if we increase the temperature, then the amplitude is actually decreasing. This is actually same type of oscillation of SDI oscillation. So we have actually 50 frequency fit, and from this we have a 2 different frequency, and from this actually we can plot the Landau Venn diagram, and if it is actually intersect around half, then we can say that this is like a pi Berry phase present. So here it is almost like our half. So we can say that in this single crystal we have a pi Berry phase. So we have a non-trivial topological sample phase. So from this also we calculate our m star, so this m star is equal to 0.18 electron mass. So this is actually very less, and we can see that this type of Dirac type of electrons are present in our sample, and we can also calculate the Fermi velocity, which is 10 to the power 5 order, and okay. So that is actually amplitude fit, but we can actually fit whole data by cos curve, and so that's what we have done here, and we have seen that the whole actually data is actually we can fit with this cos curve, and this is also at 10K and 5K data, and these are the different parameters we enlisted here. So and we have actually done the DFT calculation from our colleague, my colleague Ram Babu has done this calculation, and from this calculation what I understood that there is a band inversion between nickel and nickel D and bismuth p orbitals, and with SOC, without SOC, and with SOC almost it is like that, and this difference is very small, and so we have a non-trivial topological phase, and we have a nice 4 cross section. So we have he calculated these Fermi surface, and we have also surface state. This is surface state calculation, and this is bulk and surface, and this is surface state, and here this is the slab calculation. Here we can see that the surface state actually merged into the bulk at 4.43 electron volt. So this single crystal is actually proved that it possesses the non-trivial topological phase from the magnetotransport property and also from the DFT calculation. So next I will talk about so these are the conclusion. So next I will talk about the calcium Zn2 bismuth 2. So this is actually a Gintel structure. So there is already topological phase in Gintel structure is already reported, just like for calcium Al2 silicon 2 we have a multiple topological state, type 2 Dirac fermions and also type topological Dirac nodal line, and if we have a calcium and there are also ARPS data confirm that this is topological semi-metal nature, and we have a strontium instead of calcium. If we have a strontium also, we have actually topological non-trivial phase and pi Berry phase reported in this crystal. So there is no data for ARPS data or DFT calculation for this. It is almost same DFT, and so we don't have electronic transport measurement also in this single crystal. So we grow this single crystal, and these are the XRD data, and here you can see that here also it is polycrystalline sample, and from ritual analysis we can understand that this is the impurity free sample, and this is from this is our XRD data for single crystal sample. So here we can see that our orientation is 0, natural growth direction is actually 0, L orientation, and this is actually this is our IREX. From IREX data the stoichiometry is actually correct in our sample, that we can understand. These are the lattice parameter, and this is coming in trigonal structure with P3 bar M1. So here we have a resistivity data. Here also we can actually fit with BGM, and this is actually modified. This is the Mott term. So here also we have a electron scattering, and also Mott scattering is present, and So this is same what we observed last time or last single crystal also, but here we observed so a little bit new things. Apart from the last nickel 3 bismuth to selenium 3, here at low temperature this data is actually taking upward turn, and from this upward turn actually we can fit the, if we plot del rho by del t, so we have some minima and then actually the crossover from negative to positive. So this we define as Ti and Tm, and if we plot this actually like this, so we can see Ti is almost same, but Tm is actually changing. And this is this type of triangular diagram is already reported in this topological semi-metal, nodal semi-metal. Yesterday also Thamijal also showed this type of single structure. So we have this is semi-metal, but it cannot confirm the topological semi-metal. So we have MR in this sample. So here MR is actually at 2K we have a 100% MR is there. So little bit high, and here also this redistributed MR data can be fitted with modified Kohler's law. So this is same, and here also we fitted with modified Kohler's law, and this is the extended Kohler's law, and this is the weak anticoagulation fitting. This is weak anticoagulation. So here we have a sharp peak. And we have actually fitted with the HLN equation, and we have a alpha P factor and phase coordinate length also we calculated. So this is alpha is little bit high, and this is L phi. L phi also fitted almost like nickel 3 bismuth to selenium 3 and selenium 2. Here also this is actually 2D electron interaction is there. And this is actually here also we have actually this MR conductivity data follows the LNV rule for LNV formula. So this is also indicating the topological nodal line semi-metal. And these are the different parameters L phi and AE actually. So this is also rho x. This is the Hall effect data, and this is also we fitted with 2-band model, and we have a we have almost compensated electron and hole, and this is the mobility data. This is okay. This is mobility data, and so this is all NE and NH. So NH by NE is almost like a 1.4. And this is the Fermi DFT calculation done by Dr. Rambabu, and here we can see that we have a 3 crossing, and we have a here there is a Pani inversion between the Sb p orbital and zinc sulfide zinc S, and here we have a 4-fold degeneracy, and these are the Fermi surface, and this is actually slab calculation, and this is the Dirac point actually, and this is actually our direct nodal line. So we have here also this single crystal, this is actually Gintel phase, and here Gintel phase in this compound also we observed that it is actually indicating topological semi-metal from the magnetoresistance and also from the DFT calculation. Thank you. And this is the actual. So we have a experimental group here with Dr. G.R. Trupu, and Rambabu did all the theoretical calculation with ISAR Kolkata, Vimalingam from ISAR Kolkata, and all the data distributivity or data is we have from either UGC DACSR from Archana or Vivek Malik from IIT Roorkee, and from UGC DE Kolkata Rajiv Mandal. And Sanand actually is actually associated with this work. Now he is actually postdoc fellow in Pusan University, and he is also here in our group, Saad Narayan Pradhan. Thank you.
Any questions? Maybe I can ask also the students to put their talk in the
So I'm not from experiment, so this might be a naive question. So the Subnicot-Dihas oscillations you showed that it can be used to
get information about the pi vary phase or topological phase.
Yeah, how is it?
So actually these data we can fit, and from Landau and we actually this is actually we can get from Landau Venn diagram. So this is data we have. Okay. So we plot our we as a function of 1 by b. So we will get high amplitude near the 1 by 0 value and less at high value, and this is actually amplitude will decrease. Okay. Generally then it is Subrnicot-de-Haas oscillation if we increase the temperature. Now these data actually we can plot like we can actually get a 50 plot, and from this F50 plot we can actually get this Landau Venn diagram, and if this Landau Venn diagram will actually meet at a half 0.5, then it shows that it is actually pi vary phase. So this is this is general. In Subrnicot we can get the idea of pi vary phase. Yes.
Just want to make a comment. Your talk was so overwhelming, so many data. Start thinking about it when the slide changes.
Okay.
So please be kind to the audience and
Okay.
in the future. But I have one question. This manganese system, is it a ferromagnetic metal?
Manganese?
Sorry, the nickel system.
No, it is actually, and it is not ferromagnetic, diamagnetic.
Diamagnetic.
Yes. We have also magnetization data. From that we saw that this is diamagnetic.
Normally nickel system tends to be magnetic.
Yes, yes, yes. We have measured another sample also nickel selenium, that is also from diamagnetic ground state.
So I think we have too many data.
Okay, thank you, sir.
Maybe I can ask. So in the slide where you are showing the cross kind of oscillation, so 5 Tesla and 5 Kelvin and 10 Kelvin, there is a pi shift, like when for 5 Kelvin the maxima is there, for 10 Kelvin it is minima. Can you go after that?
This one?
No, not this one.
This is our oscillation.
Few slides. This one, the top one, left right corner. For 5 Kelvin, where it is maximum, for 10 Kelvin it is minimum. It is something like that. Is there anything to do?
Oh.
Arbitrary.
This is nothing to do. Only thing is that this amplitude is actually bigger because it is 2K. Now then you should have in 5K and 10K. If amplitude is actually decreasing like this, then this is actually signify that it is actually Subrnicot-de-Haas oscillation. Then we can go further to extract the pi vary phase information. Thank you.